Hello, and welcome to this video on process control of gas tungsten arc welding. To begin with, let me start by sharing the screen so you can follow along with the PowerPoint that I'm going to share. My name is Girish Kelkar, and I am a welding consultant operating as WJM Technologies. Additional information about my consulting business is on the web at welding-consultant.com. Let's start with understanding arc welding basics. On the right-hand side, I'm showing you a schematic. We have an electrode, and there's two parts to be welded are over here. We have established an arc, and the arc is powered by a certain amount of voltage and energy flowing through the parts, through the arc, through the electrodes, and back. So essentially in arc welding, the source of energy or source of heating is the arc itself. And so you have to strike the arc and use the arc to produce heat, to melt the parts, and in some cases also add a filler metal. One of the requirements for arc welding is the parts have to be electrically conductive. So arc welding works with metals and alloys, but not with ceramics and plastics. This schematic on the right is essentially what is gas tungsten arc welding. So gas tungsten arc welding is the most fundamental form of arc welding. Let's look at heat generation in the arc. If you look at the parameters over here, I'm showing you the schematic once again. And I have added a symbol for a resistance in the arc because that's where the highest resistance is in the circuit. And there's a current I flowing through the circuit, and it is being driven by a voltage V. All of these three parameters are linked together by Ohm's law. So Ohm's law states that voltage is equal to current times resistance. And in this case, resistance is primarily the resistance of the arc over here. The total amount of energy or power dissipated in the arc is going to be a product of voltage times current. So essentially, if you want a hotter or a cooler arc, you want to increase or decrease these parameters. The resistance of the arc is a function of multiple factors. One of the first ones is arc length. So if you extend the electrode further back or bring it closer to the part to change the length of the arc, that will change the resistance of the arc, and that will change the amount of heat generated in the arc. Another factor which affects resistance of the arc is electrode material and shape. So depending on size, diameter, and material selection for the tungsten alloy, that can change the resistance of the arc. The third factor is shielding gas, whether you're using helium or argon. Ionization voltage of helium is about 50% more than that of argon. So that means if you're using helium as a shielding gas, you need 50% more voltage to send the same amount of current through the arc. So hence, the helium arc is 50% hotter than argon. So that is why helium is commonly used when you want a much more intense heat in the arc, especially, let's say, when welding aluminum or copper, which are very conductive materials and alloys. So these are the three factors. Of these, electrode material and shape is already decided when you set up the process, and shielding gas is already decided when you set up the process. So the main control of resistance in the actual process itself while you're welding is arc length. So that is a process control that you can use in the process itself. Here's a GTAW torch, gas tungsten arc welding torch. Again, this is a schematic. We have the electrode. This is a non-consumable tungsten electrode. So essentially, the tungsten itself does not melt. And so tungsten itself remains intact. If it comes to a point where you're overheating and the tungsten particles are dipping into, or the tungsten electrode is dipping into the molten metal, tungsten can get included into the weld, and that becomes a defect. So you want to make sure that the tungsten electrode is not getting introduced into the weld. The torch provides a way of providing gas to the arc, so it protects the arc during the welding process. The torch also has electrical connections. And if it's an automated torch, it can also have cooling water, which tries to keep that electrode very cool, because we are using very high currents in automated welding. If required, a filler metal can be added either manually again or with automation, and that increases the amount of molten metal in there, and changes the chemistry and size and shape of the weld. Original name of this process was Heli-Arc Welding way back in the 20s and 30s when it was first introduced. Then during the Second World War, it changed to tungsten inert gas welding. So now T is for tungsten. That means the electrode is always tungsten, which is still true. And we are able to use inert gases, not just helium as originally was intended. So now we can use argon and helium. Recently, the name has been changed again. Now it is called gas tungsten arc welding. So that gives you the freedom to use an active gas. So the active gas which has been used once in a while is argon plus hydrogen, which provides a very clean weld in, say, austenitic stainless steels, but it is very rare. So for all practical purposes, the gas is still inert gas, and it's going to be either argon or helium or a mixture of the two. One interesting factor, which is for controlling the process, is the polarity. So polarity plays an interesting role in gas tungsten arc welding. On the left, I'm showing you a schematic where the electrode is connected to the negative of the electrical circuit, and the parts are connected to the positive. So when the electrical current flows, the electrons jump from the electrode onto the part. So that is called direct current electrode negative. So DCEN. What happens is when these electrons jump from the electrode, they end up actually cooling the electrode a little bit. And when they jump and attack the molten metal or the parts to be welded, it actually generates excess heat over there. So in this polarity, direct current electrode negative, 70% of the heat is at the part and only 30% of the heat is at the electrode. So the electrode does get hot, but not as hot as it would otherwise. DCEN is perhaps the most commonly used polarity, and it produces a deep, narrow penetration compared to the other polarity, which is DCEP. So schematic on the right I'm showing is direct current electrode positive. That means the electrode is connected to the positive and the parts are connected to the negative polarity. In this case, the heating is opposite. We have 30% of heat is generated at the part and 70% is at the electrode. That doesn't make sense. I mean, we want more of the heating at the part. So why would you use this polarity? This is also called a cleaning polarity, because when these electrons jump from the part towards the electrode, that process dissociates the oxides and produces fresh metal on the surface, which you can weld to. So this is quite commonly used in welding of aluminum and magnesium, which tend to have naturally occurring oxides, which are very hard to clean. They can be, but they're harder to clean. And the positive polarity actually helps in the cleaning of the area around the weld. One of the requirements of this cleaning polarity process is you have to use argon for the cleaning process. It doesn't work well, doesn't work with helium. So you have a choice. You can weld in electrode negative or electrode positive, or actually both. You have the choice to switch it back and forth in the process so you can get both heating as well as cleaning. So this is what you get. This is a photo of a weld where a tack weld has been made on aluminum, and you can see the weld over here. And you can see a whitish area around it, which is the area which has been cleaned during the electrode positive part of the operation. So this process was set up such that about 65% of the energy was electrode negative, and then it was switching back to other polarity and providing 35% of electrode positive. We don't need to have such a big area of cleaning. So if your aluminum is fairly clean, and you can reduce the electrode positive fraction. So we ran another experiment and ran another tack weld and increased the DC electrode negative to 95% and reduced the electrode positive 5%. And it still provided enough cleaning to make the weld. So the key is, if you do have to use electrode positive, try to use a ratio of electrode negative to electrode positive, which is the minimum required for cleaning. You don't have to use 50-50, which is commonly used. One of the downsides is if you use it 50-50 or you use unnecessary amount of electrode positive, then that can reduce electrode life because now more of the heat is generated at the electrode tip, which is not good. And also, in some cases, the excessive cleaning action can produce defects in the heat affected zone adjacent to the weld, which might show up in die pen testing. So this is an option which is interesting compared to, say, MIG welding. In TIG welding, you have the option of either going electrode negative or electrode positive or a mixture of the two. Another way of controlling the process is to use the energy in a pulsation form, which is similar to MIG welding. Over here, let's say you're using DC electrode negative, and you have a peak current for some time and it drops to a background level for some time, then it again goes up and down. So that pulsation from between peak current and background current helps to allow better control of the weld puddle. And oftentimes I've seen welders use 200 hertz as the frequency for setting it up in a pulsation mode. Pulsation mode and gas tungsten arc welding are quite common for making root passes, especially if you're having trouble with the melt drop. So root passes are commonly made with TIG welding. Sometimes it is like that. So you have the root passes made with TIG welding, and then the filler passes might be made with MIG welding or some other processes. So that is also not uncommon. The pulsation and the controlling the ratio also helps to make a vertical weld. So that allows the background current time allows the molten metal to kind of cool down during the vertical welding process. So that gives you an additional level of process control in this weld. As the name implies, gas tungsten arc welding or TIG welding requires tungsten. And of course, there are many different types of tungsten for various reasons. Pure tungsten is used, but it is cheapest, but it doesn't have very high current capacity. So that is used for smaller welds. Commonly for high power, high current welds, you end up using something like thoriated tungsten. That provides better arc start and a stable arc, but does have, the dust is radioactive because thoria is radioactive. So you have to be careful on how you are going to polish the electrodes. The other options to thoriated tungsten are zirconated tungsten, ceriated tungsten, and lanthanated tungsten. I have commonly seen people use ceriated tungsten, so that could be a good option as well. Again, these are fairly easily available from different suppliers, and they can be machined to suit. Another factor which is important in process control of TIG welding is how do you prepare the electrode tip? So you get these electrodes. Now, these electrodes are 1/8 of an inch or less, so about 3 millimeters or less. And you have to grind them to a tip. Now, you can do the grinding circular, as I've shown over here. But that's not a good idea because that changes the arc properties are not as stable when you have circular grinding. So ideally, you want linear grinding. You want to see the scratch marks from the grinding in the direction of the electrode. In addition to that, you should produce a flat ground tip with a certain tip face diameter. So combination of the combination of the tip angle, the tip face diameter, and the grinding marks makes for a good gas tungsten arc welding electrode. So that should also be specified in the part drawing for these electrodes and for establishing a validated process. Another factor which is important is not only the shielding gas by itself, but how the shielding gas flows and covers the arc. Oftentimes, you have to stick the electrode further out in order to access some hard-to-reach places for welding, and that is quite common in TIG welding. And when that happens, you need a larger nozzle. In addition to that, it would be good to have a nozzle which has a metal, what is called a gas lens. So essentially what that is there is metal wool or some kind of gauze which controls the way the gas flows out of the nozzle. So it provides uniform laminar flow. So it provides better protection of the weld of the arc and the molten metal. So to keep in mind to make sure that you only extend the tip out of the nozzle to the extent where you can provide sufficient shielding for the process. So in summary, for the process parameters, we have different arc parameters and other parameters. Arc parameters, as I mentioned earlier, is a combination essentially of Ohm's law. We have the voltage applied to the electrode, the current passing through the electrode, and the arc length, which is the resistance of the arc. And that in turn is controlled by the distance of the electrode from the part. It is also indirectly controlled by the electrode material size and shape and by the shielding gas. As we discussed earlier, helium runs much hotter than argon, so that is a choice that you have. Other parameters which control the overall process include torch angles, travel speed, pulse frequency. As I mentioned, instead of just a regular energy source, you can have a pulsed energy source, and that produces better control of the weld puddle. And of course, wire feed. If you are feeding the wire, if it's not a autogenous process, you are feeding a wire, you need to feed it at a certain rate. Gas tungsten arc welding is used both in manual as well as automated welding. In manual process, the current is controlled by a foot pedal. And so the operator who's actually running the arc is actually pressing down the foot pedal to provide a certain amount of current. The arc length is controlled by the position. So the operator can pull the torch away or closer to the weld to give it a certain arc length. And the voltage automatically adjusts to suit this electrical circuit. In automated welding, you try to control the arc length, and that arc length is controlled by measuring the arc voltage. And for a given voltage, the tip of the electrode is pushed further up or down by electric motors to bring it to a certain arc voltage. So physically, it's not actually measuring the arc length, it's actually measuring the arc voltage. But for a given arc voltage, you get a given arc length, and that's how you control the arc length. The current is programmed in the programming pendant over there. So you can control the current, you can control the voltage, and essentially you control the entire process. There are many benefits to gas tungsten arc welding or TIG welding. It produces very high quality welds, which can be X-ray quality, which is a requirement for aerospace and defense industries. It is also very commonly used for orbital tube welding for semiconductor, chemical, and food applications. And so those two industries are commonly using TIG welding process. Gas tungsten arc welding can be autogenous. So that means you do not have to add a filler alloy. You can actually weld the parts, meld the two parts themselves and weld them together without adding a third filler. Gas tungsten arc welding is very capable of welding very thin sections, and it is able to reach tight spaces by extending the tungsten electrode further out from the torch. But of course, these are very difficult, welding of thin sections and reaching into tight spaces, so it requires a lot of talent to make these welds. You can weld practically all structural metals and alloys with the right amount of energy and right filler alloy. You can weld up just about any metal to any metal. You can use gas tungsten arc welding in manual or automatic form. Both are commonly used. The disadvantages are that the deposition rate is low. Compared to other arc welding processes, such as say MIG welding, you can only put down so much metal at a time. So it takes a longer time to fill up a large weld. And secondly, greater skill is required. It's almost an art form. TIG welding is almost an art form. When you go down to welding like thin sheets of aluminum, it is incredibly difficult. So it is worth a try. If you haven't tried arc welding before TIG welding, it is worth going down to a shop, getting access to the TIG gun and try it out. It's quite challenging. In summary, gas tungsten arc welding was previously known as TIG welding, and before that was Heli-Arc welding. Essentially, the names have changed, but the fundamental remains the same, that you have a TIG torch, a TIG electrode, tungsten electrode, striking an arc to produce the welding heat. Even though now we allow for active gases, in the name it says gas tungsten arc welding rather than inert gas welding. Primarily, we are going to be using either argon or helium or a mixture of the two. Those are the two common gases. The key parameters for controlling the GTAW process is voltage, current, arc length, shielding gas, and electrode, including material, shape, and size. So all of those combined will create a certain arc, which is putting down a certain amount of heat into the weld. In addition, other parameters such as travel angle and travel speed will eventually control the seam length of the weld along the welding seam. Gas tungsten arc welding can be performed without filler, so you don't have to add a filler alloy. This is a very interesting aspect of gas tungsten arc welding. And gas tungsten arc welding can make welds that can pass X-ray, but it is slower than other processes in terms of material deposition rate. So it does produce very high quality welds, but it is a little bit slower process. And manual gas tungsten arc welding is quite difficult and is almost an art form. So this is quite a challenging process. Very fundamental, very simple to understand, but process control is challenging, and but can be done, especially for high quality X-ray level welds. There are many books where you can find resources to learn about gas tungsten arc welding, including websites. But one of the good resources is the chapter on gas tungsten arc welding, chapter 3 of the AWS handbook. AWS stands for American Welding Society. Well, I want to thank you all for listening to this video and looking at this video. If you're interested in learning more about welding and joining, please subscribe this YouTube channel. I have many other videos on this YouTube channel in different playlists, including arc welding, laser welding, resistance welding, welding metallurgy, and welding design. And so please do subscribe. And I want to wish you the very best in your efforts to learn more about welding. And thank you, and have a good day. Take care.